Hi, this is Paul from Foresight Tech. In this video, we are going to deal with the LHospitals Rule, which we can use to evaluate the limit of indeterminate forms, which is an important application of differentiation. Let's see the outline. First, I will introduce the limit of indeterminate forms and the LHospitals Rule. Then we will practice 5 questions together about how to use the LHospitals Rule. Let's see the material. Here is the definition of indeterminate quotient. And suppose we have a limit of a quotient, which we call the indeterminate quotient. And we have 2 types. Okay, the first type we call the 0 over 0. If the limit of the numerator equals the limit of the denominator equals 0. Okay, that's 0 over 0, right? That's indeterminate. So the second case is the limit of the numerator equal the limit of the denominator. Both equals infinite. Therefore, this type we call the infinite over infinite. And the both type we call the indeterminate quotient. Let's see an example here. The first, limit of sine over sine x over x. Is this an indeterminate quotient? Yes. Why? Because sine x approaches 0, x approaches 0 too, right? Both approach 0. How about the second? 2x approaches 0, x approaches 0. Okay, so it's also 0 over 0. How about the third? The same, 0 over 0. So let me highlight it first. What do we have? We have both these 3 terms is 0 over 0. And this is also 0 over 0, right? How about the answer? Can we evaluate those limits? And this time is, okay, let me see. So the first is a trig limit we learned before, right? What is the answer? 1, if you remember. And how about the second? The second we can simplify. Can we see x and the x, the same factor? We can divide it out x. Therefore, we can get 2. The same idea. So simplify, and then we can get 3. What do we get? Okay, the same type, but we get a different answer. 1, 2, or 3. That's why we call it indeterminate. Okay, because the answer is indeterminable. Okay. Look at the 2 more. So here. How about the type? And when x approaches infinity, the numerator x squared approaches infinity, right? The denominator x also approaches infinite. Therefore, this is infinite over infinite. How about this? The same infinite over infinite. So these both 2 are the second type. So that's infinite over infinite. Okay, both. How about the answer? And this time we also can get the answer directly. How? Okay, simplify the same. Okay, so divided out x, divided out x. So what is the answer? This is infinite, right? The same for the second, divided out x, divided out x. We have 1 over infinite. What is the answer? Which is 0. Can we see? Okay, so for this type is also indeterminate quotient because the answers are different. Okay, so for these questions, look as simple, right? Very easy to get the answer. However, usually we'll meet the complicated questions. Okay, how to find that kind of limit if we cannot simplify? We need a tool. Okay, the name of that tool we call the LHospitals Rule. Let's see LHospitals Rule. Here is a LHospitals Rule. And suppose we have an indeterminate quotient we just discussed, right? Either 0 over 0, the type is 0 over 0, or infinite over infinite can be found by this operation. Okay, which means we can take a derivative to the numerator, take a derivative to the denominator at the same time. Okay, don't miss this condition. If the right side limit exists, what does it mean? Okay, only when we can evaluate this limit. If we get the limit, then the left limit equals the right limit. Okay, so both limits are the same. However, if the right side limit does not exist, what do we get? Do we get the limit of the left side also does not exist? No, we do not have that result. Okay, keep in mind we do not have that result. Let me highlight. This is important. If the right side limit exists, then we can use LHospitals rule. Otherwise, we cannot use. I have one remark. Okay, and look at this notation. We evaluate the limits x approach a, the normal limit. So how about the other limit? And like one-sided limit, left-sided limit, or right-sided limit, or limits at infinity, or limits at negative infinity? Yes. So all that limits works. Okay, for LHospitals rule. Let me highlight. Okay, so this limits, or limits at the infinity, or limits at the negative infinity, all works for LHospitals rule. One more comment. Let me see. We'll look at the name of the method. We call the LHospitals rule, and the LHospitals was a French nobleman. Okay, does not mean LHospitals proposed this method. We have another Swiss mathematician. We call it John Bernoulli, who proposed this method about 300 years ago. Okay, why we have this name? There was an interesting story. Okay, and you can go Google to search by yourself. Now let's move to the proof. Here is the proof, but only for a special case. Okay, at fa equals g at a equals 0. Okay, the first condition. And the second, the derivative are continuous. And the third, the derivative of g at a does not equal 0. Okay, for the general proof, please check the textbook for detail. And now, suppose we have we go backwards. Okay, we go from the limits of the derivative. Okay, and back to the limits of the quotient, the original. Let's see. And if we work on this, we can directly substitute. Okay, the first step. Why we can directly substitute? Because here this condition. The derivative of f and the derivative of g are continuous. Therefore, this quotient is a continuous function, right? Therefore, we can directly substitute. Let me highlight. So here the first step, because it's a continuity, because of the continuity, right? And then the second, can you see? The second, we can directly use the definition. What is the derivative of f at a, which is the numerator, right? And what is the derivative at a of g? Of course, is this definition, which means the second, we directly use the definition. Okay, let me put here the definition of derivative. Okay, now what do we have? Now is what? Is the limit law. Okay, the limit of a function over limit of another function, and equals the quotient, the limits of the quotient. This is quotient law, right? Or we simply say it's just the limit law. Okay, quotient law. And if we're going to here, we can simplify. How? Okay, this is easy to simplify. Can we see? And this denominator and this denominator are the same, which means we can times x minus a, both numerator and the denominator, and then we can simplify. After simplify, we get this. Okay, so this step, we just simplify, right? How about now? So because we have a condition, can you see? We have a special case, fa equals ga equals 0. Okay, so what do we have this time? fa is 0, ga is 0. Therefore, we have the last, right? Can you see? So what do we get? Now we get from the beginning, see, and we're going to the end. What does this mean? This is a L'Hopital's rule, right? Okay, definitely. So this is the simple proof for this special case. Okay. Now let's go to practice L'Hopital's rule. Here is the first question. See, we are familiar with this limit, right? And we learned before. We call the trig limit. Let me go to see here. We call the trig limit. And we also know the answer is 1, right? We have this formula. And up here, we just going to verify if L'Hopital's rule works for these questions, for the answer. Let me see first. Is this indeterminate form? 0 over 0? Yes, right? So what we can do? We can use L'Hopital's rule. Let me see. We can use L'Hopital's rule, right? Okay, if I use L'Hopital's rule, so we can do this. We can take a derivative to the numerator and take a derivative to the denominator. Okay, and then we're going to find the derivative, which means now the denominator goes to 1, right? The numerator goes to cosine x. Cosine x is continuous. Therefore, we can directly substitute, which means that the limit is cosine at 0. Cosine at 0 is 1. See, definitely, that's true, right? Okay, so, and we see L'Hopital's rule works very good, right? Let me see another question. Here is the second question. Is still a limit of a quotient. So first, let's see if this is an indeterminate form or not. And we plug x equals 4 to the numerator. Can we see 4 squared 16 minus a, what do you get? We get 0. Okay, denominator 4 minus 4, what do we get? 0. Okay, so this form we know, okay, is exactly 0 over 0, right? So we can use L'Hopital's rule, no problem. But we do have an old method. Do you remember? Let me first show the old method we did before, and then we can compare. Okay, the old method we did before is do this, and then we can factor the numerator, and then probably we can simplify this fraction. Okay, we follow that idea, which is this. We're going to factor the numerator. What do I get? I get x minus 4, right? Times x plus 2. The denominator is x minus 4. See, exactly. We can simplify now. Divide it out. And divide it out the x minus 4, both numerator and the denominator. Therefore, what do we get? We get this. And we get the limit x approaches 4. Now we only have x plus 2 left. And this is a polynomial directly substitute, right? So we have 4 plus 2. And the answer is 6. Okay, this is the old method. Of course, we just discussed, and we can use the new method that we learned here, which is L'Hopital's rule, right? Let me see. If we use the new method, can we get the same answer? Okay, and we are going to use what? We use L'Hopital's rule. Okay, and like this, I put so L'Hopital. Okay, it's a rule. And what do we do? So we're going to do this. We're going to take a derivative to both the numerator and the denominator, which means x squared minus 2x minus a, take a derivative. The denominator x minus 4, take a derivative. That's L'Hopital's rule. And then now, this is easy to calculation, right? To find the derivative. Okay, the derivative of the denominator is 1. derivative of the numerator, which is 2x minus 2. And then this polynomial directly substitute, which means 2 times 4 minus 2, right? And 2 times 4 is 8. 8 minus 2 is 6. That's good. We definitely get the same answer. Okay, so we verify LHospitals rule again. Now let's see another question. Here is the third question. Okay, so we have a limit of a quotient. Let's going to verify is this indeterminate or not. Okay, and the numerator lnx of course approach right grow into infinity. So this is infinity over the denominator also goes to infinity. Therefore, this is a indeterminate form. What we can do, we can use a LHospitals rule, right? So we can use a LHospitals rule. Okay, let me going to show LHospitals rule. Therefore, we can take a derivative, right? Let me take a derivative to the numerator. Take a derivative to the denominator. I will going to find the limit, the derivative. Okay, and what the derivative of the numerator, which is the natural log, and therefore we have the reciprocal, right? And denominator is a power. We have a 2x, and this fraction we can simplify, and therefore we have this kind of x approach infinity. Now we have another fraction, which is 1 over 2 times x square, right? We times x to both numerator and the denominator. Now we can easily to get it is 1 over infinite, which means 0. Okay, so easy to get if we use a LHospitals rule for this question. I will give you another comment. Okay, for this type of limits, this is famous. Okay, let's look at the function. The numerator we call the log function, right? The denominator we call the power function. Here is a special power. Okay, so we can do this. We can get a general result if I change the power 2 to any other positive powers. Let me write it here, which means we have these kind of results always true. You can use the same method. We use ln, this log function, over x raised to the nth power. Okay, always equals 0 for any positive power. Okay, you can use the same method. Let me highlight this. What does this mean? What does these results mean? Okay, with these results, okay, we get a very famous result. Can you see? And the log function grow into infinity. The power function also grow into infinity. If the ratio equals 0, which means what? Who goes up into infinity faster? Of course, the denominator, which means the power function grow into infinity faster than the log function. Does this make sense? Or I draw a graph. Okay, I draw a graph so you can see like this. I draw this is x and this is y. I put the log function. So log function like this. The grow up into infinity. Okay, but it's not so fast. This is y equals ln x. And I will draw the power function. Okay, I give any power function. Power function will grow like this, right? And this is y equals x raised to the nth power, any positive number. Okay, can you see? We can get a feeling, right? And the power function grow up much faster than the log function. Or I draw another 9. So you can see in this way. And this is x. If we take x approach into infinity, and you can see and that ratio equals 0, which means the distance between these two functions, this distance will cover the major part of all the whole distance, or the distance goes to infinity. Okay, that does make sense. Now let's do another question. Here is the fourth question, and the first let's verify this is indeterminate quotient. Okay, and the numerator natural exponential function, of course, grow into infinity, right? So that's infinity over the denominator x squared goes into infinity. Therefore, this is an indeterminate form, right? So what do? We can take a derivative, which means I can use LHospitals rule. Okay, LHospitals rule. I will going to take a derivative. So, and this time I skip one step. I directly take a derivative. Okay, and the ex take a derivative is itself. X squared take a derivative equals to 2 times x. Now have we get the answer? No. Why? Let's go to check this fraction again. See, and the numerator still goes up into infinity. How about the denominator? 2x still goes up into infinity. What does it mean? So we still have an indeterminate form. Okay, what we can do? We can use a LHospitals rule at the second time, right? So let me show here. So the first time we use the LHospitals rule, and we get the indeterminate form. We have to use the second time. Okay, so I will going to use the second time. And in the future, no matter how many times, okay, you can use, no problem. And I directly take a derivative. Ex take a derivative is itself. 2x take a derivative is 2. Very good. This time I get the answer. Why? I directly put so now I have this 2 is here, and the numerator goes to infinity. Therefore, I have the result is infinite, right? Okay, so I get the answer. The same, I have a comment for you. Okay. And we'll look back. What is the numerator? This is an exponential function, grow up into infinity, right? And the denominator is a power function, also grow up into infinity. This is a special power. However, we can extend it into a general. Okay, so let me show you the general results. Is like this. So we can get a limit when x approaches infinite, okay, ex, which means a exponential function, and the power are generated into any, no matter it's positive or negative this time, okay. And see, the result is always infinite. Okay, let me highlight. This is a general result. I will show what that is mean to you. Okay, and this means what? Means exponential function grow up into infinity faster than the any power function, right? Both increase into infinity, but the result is infinite, which means the numerator goes up into infinity faster than the denominator. Power function, exponential functions are much faster. Let me draw a graph, okay, so you will see it clearly. Let me draw a graph as the last time we drew the last example. If this is x and I draw like this is y, okay, so I put the power function first. The power function is like this. The power function will goes up into infinity, okay, in this way. Let me put it like y equals x raised to the nth power. How about the exponential function? The exponential function will goes up into infinity in this way. Okay, for example, this is 1 and then goes up and then goes up much faster. Okay, so I say this is y equals e raised to the x power. Okay, so we can see, right, the exponential function goes up into infinity much faster than the power function, any power function. Or if I put this, if I put this 9, okay, when this x goes up into infinity, okay, and the same, the power function, exponential function, goes up into infinity much faster than any power function. If we put the last question and this question together, see we have these results. Among exponential function, power function, and the log function, which one is the fastest? Goes up into infinity. Exponential. Which one is the slowest? Which is the log function, right? And the power function is in the middle. Okay, this is a famous result. Then now let's practice one more question. Here is the last question. Okay, so the same. First, let's verify this is indeterminate. Okay, so the numerator, of course, square root of x goes into infinity, ln infinity goes into infinity, right? So that's infinite over x squared goes up into infinity. Therefore, we can use LHospitals rule. See, we can use LHospitals rule. Okay, and now we're going to take a derivative. And let me write the complete. Take the derivative to the numerator and take the derivative to the denominator. Okay, so we're going to do calculation now. Okay, so what is the derivative of the numerator? Okay, this time a little bit complicated. Can you see ln square root of x is a composite function? So what do? We have to use a chain rule, right? It's okay, we use a chain rule. Therefore, we have the derivative of the outer times the derivative of the inner. The outer function is ln u, right? The natural logarithm. Therefore, we have a reciprocal, which is 1 over u. U is a square root of x. This is the derivative of the outer. The derivative of the inner function is a square root of x. Take a derivative is 1 over 2 times the square root of x. Okay, so now what is the denominator, which is 2x, of course. We have to simplify, right? Let's simplify. What do we get? Okay, so we times 2x, okay, so what do we have? So 1 over 4, right? And the x times x, we have x squared. Okay, what's the answer? That's 1 over infinite. Therefore, the answer is 0. And that's all. Thank you. I hope you enjoy learning on this topic. If you have any question, please leave your comment. If you like this video, please give me a thumbs up. Thank you for your support. Please don't forget, you are very welcome to subscribe to my channel for more videos. In the next video, let's see. We will deal with the indeterminate product using LHospitals rule. Hope to see you there. Thank you. Have a nice day.